Everyone, welcome back to the channel. In this video, we'll be discussing about the last problem of today's weekly contest, maximum segment sum after removals. The problem states that you are given a zero indexed array nums and some number of queries. What you need to do is this query denotes that you will be removing a particular index from your initial array, and you need to find out the maximum segment sum after applying the ith query. So you need to do this for every I. So let's take an example. Let's say this is the array 1 2 5 6 1, and you the first query is 0, which means that remove the 0th index, which means remove this particular one. Now, if you remove this, there is one segment. Segment is nothing but a continuous set of indexes. So there is one segment, and because there is only one segment, what is the segment sum? Segment sum is 2 plus 5 plus 6 plus 1, which is 14. And because there is only one segment, the maximum is that segment only. Hence, we return 14. Now, let's say second query, which is 3, which says that remove 6 from your array. Now, if you remember, we have already removed 1 and now we have removed 6. So what we are left with, we are left with 2, 5 and this one. Now you can see there are two segments. One is 2, 5 and one is 1. So sum of these segment is 2 plus 5, 7, and sum of this segment is 1. Maximum of 7 and 1 is 7, and hence 7 comes here in the output. Now similarly, when we remove 2 as well, which means we remove 5. Now we have removed 1 already, we have removed 6 already, and now we are removing 5 as well. So there are only two elements left, 2 and 1, and these two are part of two different segments because they are not contiguous. Now the sum of first segment, which consists of 2, is only 2. Sum of second segment is 1. Maximum of 2 and 1 is 2, and hence 2 comes here. So hope the problem statement is clear. Now, before jumping into the solution, I would like to highlight that there are multiple possible solutions for this problem. We will try, like as always, we will try to simulate the problem and see if we can come up with some optimizations to solve the problem by just simulation. So that we will look at. But there is one more interesting solution to the same problem using disjoint set union. Though you can see DSU is something which is not clearly applicable here, we will look at approach that can, like, that is possible in these kind of problems. Like the approach would be common. You can use that approach in many other problems. So I will also discuss that approach in the end of the video. So I would request you to stay till the end, and I am sure you will learn something new from that approach because that approach is used in solving a lot of problems. So with that note, let's start. So first of all, we have this array, right? And let's try to simulate whatever we are given. So we are given that we are removing a particular index from the array. Now what is happening after removal? So initially there is only one segment, like the entire array. Now we remove something. So after removal, what happens is we have two segments, like at max two segments. Now let's say there is another query comes which says that remove this element. In that case, this larger segment would no longer be valid. Instead, there will be two smaller segment, right? Now let's say another query come which says that remove this element. Now again, this larger segment would no longer be valid, and this time instead of breaking the segment, we have like only one segment formed. So what is happening? There are only two cases. One, by removing an element, we will form two new segments. Second, by removing an element, we will form one new segment. Right? The previous segment will be destroyed and we will form one new segment. And there can be cases where there are no new segment formed. We will look at that as well, but let's just ignore that because if nothing is found, nothing can be contributed to the answer. So what we need to do is, let's say let's try to apply the brute force approach. Okay, now what we need to find the maximum segment sum. So after removal of an array, after removal of an index, what we can do, we can iterate over the entire array, find the sum of the segments. Let's say this is s1 and this is s2, and then just take the maximum across all these segment sums. So what you are doing for one query, like after removal of one query, what you are doing, you are just iterating over the entire array and then finding out these segments and their sums. So in a way, for a single query, you are iterating over an array of length n, and there are total q number of queries. So complexity would be order n into q. Now you can see the value of n and q both are up to 10 to the power 5. So if both are up to 10 to the power 5, this solution would surely not work. Now notice that you can't remove this q from the complexity. So you have to remove this n from the complexity. So here is where our observation will come. So what we have just said, that removal of an index only affect one segment at a time, and instead of that segment it will introduce some newer segments in the in our set of segments. So instead of reiterating over the entire array, so this, if you remember, the complexity was n into q, and this n was coming from, because we are recalculating all the segment sums. So we are saying that only one segment sum is there, which is removed after removal of an index, and with the removal of that segment sum, we will introduce some new segment sums in our set of segments. So instead of reiterating and give and paying this order and complexity, we can just say that if we are able to find this segment, like let's say we are able to find this segment, then we can just simply say that after removal there will be two new segments. And what we can do, we can maintain a set of integers which contain the sum of segments. So initially the set will be empty, or sorry, set will contain the one only one segment which contain the sum of all the integers. So initially the set will contain sum of all the integers. Now once you remove some element, you will remove the original sum and add back two new segments. So for example, let's say the set contains initially you remove this, so there are two segments. One is this entire piece, and second is this entire piece. Now, because there are two segments, you have two element in your set. Let's say it is some x and y. Okay, x denotes this part and y denotes this part. Now you get a query to remove this element. So if you remove this element, what you are doing is you are removing this segment, because this segment is no longer valid. So what you will do, you will remove y from your set and instead add y1 and y2, where y1 is the segment sum of this part, and y2 is segment sum of this part. Now if you are able to compute y1 and y2 without iterating over the array, you can skip this order n in the time complexity, right? So how to compute y? Let's say somehow you know this l and r. How you know this, will come to that, but let's say somehow you know this l and r, that is the starting point of the segment which this newer removed element belongs to, and the ending point of that segment. So if you know l and r, can't you compute y? You can, right? Because computing y will just be a matter of computing the sum of l to r, which will be calculated using prefix sums. Now once you have calculated this y, you can just remove y from your set. Now to calculate y1, it is also very easy, because you know this index I. Index I is something that you are removing, right? So you know this index I, you know L, so you can easily calculate the sum of L to I minus 1, right? And similarly, you know I plus 1 and you know R, so you can easily calculate the sum of I plus 1 to R. So you also calculate the sum of like you also have y1 and y2 easily. Now once you have these three things and you have removed y and added back y1 and y2, your job is done. Now you have a updated set of segments and you can just find out the maximum. And if you maintain a set, you can, or any other data structure that is ordered, you can just return the last or the first element depending on which the order is you are maintaining. So you can remove this order n and just do three operation, right? So but there is a catch here. Now we have assumed that we know L and R, but how can you know L and R? What is L and R? L and R is the segment which actually contains the removed element I. So we are removing an index, right? We are removing an index I. So we need to find out a segment which contains I. How to find that? That's the only question. And once we have L and R, we have just saw that we can calculate Y, we can calculate Y1, we can calculate Y2. We will remove Y from our set, we can add Y1 and Y2, and hence we will have a set of the new segment sums and we can return the maximum among them. So hope this point is clear. Now only thing that remains is how to calculate this L and R. So let's focus there. So first of all, what let me just get rid of some of these. Yeah, so let's see. Now we have to find out what this L and R are. So what is L? L is nothing but the index which is removed just before I, right? Similarly, R is nothing but the index which is removed just after I. So let's say there are like the array is a lot bigger than this, and this element is something which is removed in the previous iterations. So what will be the value of R? R, the value of R would be this index in this case, and the value of L would be this index. So how to calculate it? You can, what you need to find is the index which is smaller than I and is removed. And how to calculate R? The index which is greater than I and is removed. So how to do that? What, let's say you maintain the set of uh, removed indexes. So finding I would just be a matter of finding a upper bound and the lower bound on this set of removed indexes. So let's say there is a removed index set which contains only the removed indexes. Now you are newly like you are maintaining this set. So you this set contains, let's say this is I2, I1 and this is I2. So this set, the set that you are maintaining contains I1 and I2. Okay. Now you are removing index I. So what you can do, you can just do a lower bound or upper bound on this set and get I1. Similarly, just do like the next element would be I2. Now, once you get I1 and I2, you can just do I1 plus 1 to get L and I2 minus 1 to get R, right? So that's how you will get L and R. So in a way, what we need is two data structure. One data structure that can maintain this thing, which is like deleting an element, and then finding the maximum element because we need to find the maximum segment sum at the end, and it can also hold duplicate. So for this thing, like the first thing that we have discussed, we will use multiset, right? Now why duplicates? Because these are the sums of the segments and sum of segments can repeat. So that's where the for the first piece we will use multiset. Now what about the second one actually is interesting, that duplicate is not required, deleting is not required. We just need to insert an element because and we need to find the lower and upper bound of a particular element in. So for this a set can be used. So we have two data structure, one data structure to maintain the sums, second data structure to maintain the removed indexes, and we will use we will use the data structure to find out L and R. And once we have L and R, we will use the first data structure and remove the indexes or the sums of already existing segment and insert the sum of newly formed segment. Okay, so hope the entire solution is clear. Now just let's just look at the pseudocode to make it more clear. So let's see. So this is how the pseudocode looks like. As we said, we have two data structure. One is a multi-set because this will hold the sum or sum of segments or sectors, right? And remember, this is long because some can exceed the integer limit. Now, second data structure is set of removed indexes. Okay. Now, for each query, we are finding out L and R. How to find L and R? We will use this set data structure which contains removed indexes. So we can just find out the element which is just greater than removed index, and we can find out the index which is just smaller than removed index, which is q, and do -1 for this and +1 in this. So that's how we find L and R. Now we can just erase, like we'll use, now you have just find, okay, let's go to the diagram. So you have just find L and R. So what you need to do, you need to remove this Y, right? So that's what we are doing. We are removing this sum of L to R from the sectors, and you are okay. So initially it is wrong. It will contain the sum of entire array, right? The sum of entire array, and then you are inserting the sum of L to Q minus 1, like here I is equals to Q, so you are inserting this sum L to Q minus 1 and I plus 1 to uh, I plus 1 to R, which is Q plus 1 to R. Now you are inserting these two sum. Now notice that this can only be inserted if L is less than equals to Q minus 1. So it may happen that you are removing this index, and if you are removing this index, the index before it is already removed. So there is no new left segment that is formed. So you have to do this or do this insertion only when L is less than or equals to Q minus 1, right? And similarly, you have to do this insertion when Q plus 1 is less than equals to R. Now, once you have done these two insertion, you have like your set of sum is updated with the new set of segments. So what you need to do, you need to just return the maximum of this set of segments. So you just take the maximum and insert it in your result. And finally, because you have just now removed a new element. So what you will do, you will just insert that new element in your removed indexes. So what will the time complexity? What you are doing a binary search for finding L and R. So that would require log n time each. Okay. And then you are erasing an element from a multiset and inserting two element in the multiset, that each of these would again take log n, right? Where n is the number of elements already present in the set, which in worst case would be n only. And then this insertion is also something which is login. Okay, so in a way, like you are applying login multiple number of times, but it is very well constant, and number of queries is q. So the complexity would be q log n. So remember, we have started with q into n, and with a single observation. That observation, what was the observation? That we don't need to iterate over the entire array, because a query will only interact or will only affect one single segment. So with that observation, we have reduced our complexity from n log n to q log n. So let's just quickly look at the code, and then we will look at the disjoint set union solution for the same problem, which is more interesting than this. So like this is the prefix sum, nothing new here. We are maintaining the multiset, and initially multiset contains prefix n and 0. This 0 is something I have put, but it's not required really. Then we have so this is required when all the elements are removed. So this you will, if you implement this, you will understand why this 0 is required. When all the elements are removed, you are doing this all dot r begin, like the maximum, you are finding out the maximum, right? So if there is nothing in the set, this will fail. So either you tackle this case separately or just insert 0. That would take care of this case. So it's very small implementation details, you can figure it out. Now this is the first data structure. Second data structure is removed indexes, and this is the result. Now because we have converted everything to one based indexing, I am doing I++ here, and then we are finding out the r here is the upper bound of I, and we have assumed that r is n, the last element. But if there is a element after I in our removed indexes, then we will reduce our last index to that particular index -1. And similarly we are finding out the start index. So just before this removed index, there will be L. So what we are saying is, if it is not begin, then just before this was the L, lth index. So we are doing minus minus and finding the L index like this. Now we have L and R. Now we find out the range sum and then remove it from the initial data structure. And then we are inserting start index or L to I minus 1 and I plus 1 to R. And as discussed, we have to take care of these cases, because otherwise, like if it exists, then only we will insert, otherwise we will not insert. And finally, we are pushing back the maximum element. What is the maximum element? The by default set is sorted in ascending order. So the last element would be the maximum. So I am doing R begin, which is the reverse begin. So what this will give us the last element of the set, and inserting the newly index I, which is removed. So hope this solution makes sense. Now let's just look at the other solution for the same problem. Okay, and this is even more interesting, and you can apply this concept to lot of other places, because where you can't actually simulate it. So here we are able to simulate the problem, like we are able to simulate the problem forward. That is, when we are removing an index, we are able to find out what all things will change, right? But there may be the cases, or there may be problems where you will not be able to find out what are the next, like what are the impact of your query. So in those cases, what you will do, you will do reverse order, like you will answer the queries in reverse order. How? Let's look at it. Let's say there are four queries. The first query says that remove this index, second query says that remove this index, third query says remove this index, and fourth query says remove this index. Now remember that queries like this solution, whatever we were discussing, will only apply when there is some kind of merging happening, right? So here, instead of merging, like there are two things, right? Like uh, either segments will merge, right, or they will get a disjoint, like, or unmerge, right? So here segment got broken. Like whenever we introduce a query, a previous segment which was there was got broken. So we don't know a data structure that can uh, broke things efficiently, but we know a data structure that can merge things efficiently, which is disjoint set union. And that's how this solution would come. What we will do, instead of coming forward, that is, after removing an element, we are breaking the segments. Instead of doing this, what we will do, we will break all the segments. That is, we will apply all the queries at once. One, two, three, four, we'll apply all the queries. Now we form, like we have some segments. This is one segment, this is one segment, this is one segment, and this is one segment, right? So now you have some segments. So what you will do, instead of merging, instead of breaking the segments, you will remove indexes one by one. So you, the last query was 4, so you will say that okay, now query 4 is not there. So if query 4 is not there, this index is alive. So if this index is alive, what you are doing, you are merging two segments. So this is one segment, this is one segment. Now you are merging two segments. And that is what we have a data structure for, which is disjoint set union. And that's the overall intuition of this solution. Now let's just dive in. So first of all, as we discussed, we will break everything, because we know how to merge, but we don't know how to break. So that's where we break everything. Now, after breaking, what we get is we get these relations. So there is only one. Like there is an isolated node one. Like if you know DSU, I assume that you know DSU. If you not, I will recommend you to watch that and then rewatch this video to get this concept. uh, we have also discussed GSU in other solution of the same channel. I will link the video as well. So we have broken the elements, like broken the segments, and this is the final result. So this crossed one are the ones which are altogether removed. Now this joined ones are the ones which are uh, joined, or which exists in which exist together after every breakage. So 0 exists in itself, 2 exists in itself, 6 and 5 exist together, and similarly 8 and 9 exist together. Okay, so now let's say like after this you can answer the fourth query or the last query, because, which says that what will be the state after applying all the queries. So you can answer that. Now you will say that okay, I will remove 4 because I want to answer the third query, right? So I will remove 4. Now once you remove from, what happens? 1 becomes alive. So this becomes alive. So let's okay. So what we will do? Let's remove this. So this becomes alive, and you have merged these two as well, right? So in a way, you have formed a new like this new sets. So previously 0 was there, 2 was there alone, and now you have alived one and you have merged these three. And this can be done easily using disjoint set union in approximately order one operation. Now once you have joined this, you can answer the query. Now similarly, once you have answered the third query, you will remove 3. That is, you will alive 7. Now once you alive 7, what happens? Again, 5 6 existed previously. 5 6 will merge with 7, so this will come. And similarly 8 9 existed, and this will also merge with 7, so this will come. So in a way, uh, this is the new set which is getting formed. Again, this can be done easily using disjoint set union. Now you have answered, like now you will answer second query. Now you have answered second query, so you will just remove this to answer the first query, which means that you are aliving 3, and you are merging 3 with 2, and you are merging 3 with, okay, you are merging 3 with 2, you can't merge 3 with 4, so that's the only edge. And now you can answer the first query. So hope this solution also makes sense. I can go through the code quickly, but I will strongly encourage you to think about the solution once more yourself and implement it yourself, because this will give you a lot good understanding of disjoint set union, and you can apply the disjoint set union in lot of other problems if you uh, apply this approach on and you have implemented this approach yourself. So let's just quickly look at the code of this as well. So this is the disjoint set union piece, which we will not discuss in this solution. I hope you understand what is DSU. Now, what we are doing, as discussed, we are applying all the queries. So basically, we have already applied all the queries. It says that we have removed all the things already. Now, what we are doing after removing, we are merging the things which needs to be merged. So if you remember, we have started with 5 and 6 already merged, and 8 and 9 already merged. So this merging is something that we are doing in this loop. So what we are saying is, until we hit a 0, we will merge everything. Okay. Now once we have merged everything, we have formed our initial sets. Now we can answer the last query. Last query would be just the max value of the current configuration. Now once we have answered the last query, we will remove the last query so that we can answer the second last query. So this is the index that we need to remove. Like we have already removed, now we need to alive this index. So what we are doing is, we are updating the value of this index with the original value. Remember, after removing, we are just keep like assigning it to 0 so that we make sure that there is like this is removed. So now we are aliving this index. Now once you alive this index, you have a new set, right? If you remember, 4, let's say you alive 4. So if you alive 4, initially there is no node named 4, but once you alive 4 there will be a node named 4, right? So that's what we are doing here. There is a node named index which has the value this, and because this is a newly formed node, it can affect max value as well. So we are updating the value of max value of DSU like this. And after this is done, what we have to do is, just let's say you have removed this 7. Okay, so what you have to do, you have to just attach it with the previous and the next element. Now again, you will attach it with the previous only when this is alive, and similarly you will attach it with the next only when this is alive. So that's what we are checking here. If it is alive, like if it is not 0, it means it is alive, then only merge this, and similarly if the next one is alive, then only merge this. Once you have done all of this, you can just like you continue, and then the current max value will be the answer of the previous query, and you can continue this loop and get the answer of all your queries. So hope this solution also makes sense. Let me know if you have any doubts in any of the solutions. I would be happy to answer. And if you like the video, give it a thumbs up. Do share with your friends. And I would encourage you to share this, because this approach would help a lot of other people to understand the disjoint set union and it's working correctly. And finally, if you haven't subscribed, do subscribe to the channel, and I will see you in the next video. Thank you.